As I said, our last speaker is Eleanor Hall from Berkeley. Please take it away.
Hi, everyone. I just want to say thanks to the organizers. I'm sorry to not be there in person like I was planning, but COVID. I'm going to be talking today about some recent work I've done with Juna Kroon and Hitoshi Murayama on non-perturbative methods for false vacuum decay. So we've heard a lot of great talks. Oh, there we go. We've heard a lot of great talks over the course of the last week about how exciting gravitational waves and phase transitions are. And so I'll go over this a little quicker than usual. In particular, gravitational waves pose our only direct way of probing the very first second of the universe, during which prior to the formation of the CMB, the universe is opaque to photons, but not opaque to gravitational waves. So any gravitational wave signals formed in this era may still be able to propagate and stay lurk until the present day when we could detect them. And one really exciting form of gravitational wave signals are gravitational waves from first order phase transitions. And these first order phase transitions proceed through false vacuum decay when the high temperature vacuum becomes a metastable local vacuum. And then will decay to the true vacuum with some characteristic rate and critical temperature. This triggers bubble nucleation, and these bubbles expand and collide, and the violent aftermath will produce a gravitational wave signal, whose rough shape will tell us about the characteristics of the theory that produced it. And these signals, could be detected at most notably LISA, but we've also heard a bunch of great talks about pulsar timing arrays and all the other exciting gravitational wave experiments that are ongoing and coming up in the next few decades. But our ability to get any sort of information out of a signal that we detect in the future is limited by our ability to predict these signals given your favorite beyond the standard model theory. And in particular, the very first step of this process, namely calculating false vacuum decay rates, is our current existing methods for calculating them are flawed. And in particular, kind of two ways in which we run into problems are that the usual technique that people use to calculate false vacuum decay rates are all perturbative. And so naturally will fail for strong couplings. So I'm in particular interested in QCD-like theories. And if you try and sidestep this issue using effective models, you get wildly inconsistent results. So you can't really trust them, which makes sense. It's hard to sidestep non-perturbativity. And as we heard from Ollie's great talk earlier this week, even for models that are well within the perturbative regime, the usual finite temperature perturbation theory will give you huge uncertainties because of this unphysical scale dependence. And so these are kind of big problems with the typical methods that people use to calculate gravitational wave signals, and particularly false vacuum decay rates. So as theorists, there's a lot of work to do before we can make reasonable predictions for our whole range of theories. So I'm going to start by kind of walking through the usual perturbative way of calculating the gravitational wave signal, and try and move a little more pedagogically than I normally would. But I'm going to start from a place that many of you might not be familiar with, and that's this non-perturbative first principles definition of the false vacuum decay rate called the direct method for false vacuum decay. And this is by a couple great papers by this group here at Harvard. And basically, it defines, they derive this expression for the decay rate from first principles and get this expression in terms of this ratio of path integrals here. And so some important features of this path integral is that here, this notation on the integral denotes this boundary condition at t equals plus or minus infinity, which is typical for false vacuum decay rates. Kind of one of the novel features is they have this delta function in the numerator that restricts the time of that the field configuration inside the path integral crosses the classical turning point. And so what this means is that the numerator is going to look kind of bounce-like and give you the usual kind of ratio of bounce solution to false vacuum. And the last piece of this is that this is all in Euclidean space. And so there's an analytic continuation from Euclidean back to Minkowski, where first you evaluate time to be real and then analytically continue. And within this formalism, the imaginary part comes out much more straightforwardly than it usually does in your usual perturbative definition of the false vacuum decay rate. Because as we analytically continue, we'll just get an imaginary part out of this delta function. And so this actually simplifies that analysis quite a bit. But there's the tricky question here is how do we evaluate these path integrals with these boundary conditions and delta functions? And so this is why this is actually difficult to evaluate. In the usual perturbative method, we can do this relatively straightforwardly. And up to some finer details, basically we can expand in the saddle point approximation and apply these boundary conditions and delta functions just to the classical field around which we're expanding. And if you do this, which I'm not going to walk through, you get something that you get your exact usual perturbative expression, where here I've conveniently hidden all the annoying factors like the fluctuation determinant and this prefactor, because I don't want to get bogged down in them in today's talk. And we have the exponential with the usual action of the bound solution and the constant false vacuum solution. And you can basically just see this in the expression here. Because of this delta function in the numerator, the dominant saddle point that will dominate this, the numerator, is the bounce saddle point. And we can imagine that the region, here I've made this little plot where the black line is the saddle point. The shaded region is kind of roughly supposed to represent what we might imagine the wave functional would look like, where a characteristic fluctuation around the saddle might look something like this pink squiggle here that I've scribbled. And similarly for the denominator, we don't have this delta function, and so the dominant saddle point is going to be the constant false vacuum with similar little fluctuations around it dominating the path integral. So this gives you this usual expression. This does take into account fluctuations up to Gaussian order, even though this is just the classical action here in the exponential. But that means that we're limited in our ability to treat radiatively generated phase transitions. So usually what people do is we kind of go from this expression to the one loop expression, where naively we might say, okay, well, what if we substitute an effective action in there? And in particular, if we consider, thinking here about some generic scalar theory, like a single real scalar, this will give you one loop Coleman-Weinberg potential at zero temperature that looks something like this. And so you can kind of go through naively, insert this into the exponential, at least fairly straightforwardly. And there's some other complications, but the thing I want to think about today as a complication is that there are these unstable parts of the potential corresponding to this barrier region here, whenever you have a first order phase transition. And in those regions, V double prime is less than 0. And so if you come and look at our Coleman-Weinberg potential, that's going to give you, in certain parts of this integral, a log of a negative number. So we get an imaginary part out. So that doesn't, at least in this construction, we don't really want that. So we might say, oh no, where's this imaginary part coming from? The basic idea is that it turns out that this imaginary part, right, since it's being generated by these unstable regions, is coming actually just from non-local fluctuations path integral. So what do I mean by that? What I mean is that for a given mean field here in our potential, like the field that we plug into our potential, what's going on in the path integral, right, is we're integrating over some sort of like wave functional situation. And so if we have a local fluctuations around that mean field, here represented by the dotted line, we would imagine it's kind of this Gaussian looking thing around that mean field. But for these unstable regions, the energetically favorable wave functionals are actually going to be these non-local superpositions of the two different local vacua. And so these non-local contributions are actually what's going to generate this imaginary part. And we can see this by just seeing that the real part is generated by the region where the fluctuation operator, which is kind of the inverse scale of fluctuations, is greater than 0, and the imaginary part is when it approaches 0 and is less than 0. So these are actually cleanly separated. The imaginary part is purely generated by non-local fluctuations, and the real part is purely generated by local fluctuations. So if we were to kind of sloppily drop the real part, or drop the imaginary part and just take the real part of our one loop potential, it actually gives you the correct thing, because this blue real part is what we saw in the numerator of the direct method, local fluctuations around the bounce solution. So this one loop approach, there are some other issues with it, but it actually, at least at 0 temperature, it gives you roughly what you want if you do the naive thing of dropping the imaginary part. So this is all well and good, but we're still working in perturbation theory. And what we'd love to do is go beyond perturbation theory so that we can treat strongly interacting theories. And one way to do this might be to use tools for exact effective actions to calculate effective actions non-perturbatively. My favorite one of these is the functional renormalization group, which flows non-perturbatively from your classical action to an exact 1 pi effective action. I'll briefly kind of introduce the idea of the functional renormalization group. The basic thing that you do is you add this regulator function that freezes out IR modes below some scale k. So at high scales k, this freezes out basically all modes. And if you go write down your scale dependent effective action, you get the classical action. Conversely, as you take k to 0, all modes are active and you get the full 1 pi effective action. This scale-dependent effective action, though, obeys this exact flow equation that allows it to flow it across different scales k. And so coupled with robust approximation schemes that aren't based on perturbation theory, we can flow the scale-dependent action from the classical action to the 1 pi effective action. So this has been really effectively applied in the last decade in QCD, both for calculating quantities like the phase diagram and also for more dynamical quantities, like very closely matching lattice results, but without requiring the full computational power that lattice does. So that's a pretty exciting thing that we'd love to apply to phase transitions or to gravitational waves and fault stacking decay. But the problem is that either with the FRG or with other methods, effective actions that are computed exactly are fundamentally convex. And this comes back to the idea of these non-local fluctuations. In particular, because these effective actions integrate over all fluctuations, are not expanding perturbatively around some point, these non-local configurations will essentially interpolate between the two local minima, so that this is what's referred to as the Maxwell construction, so that the potential ends up just totally flat between two local minima. So this obviously isn't something that we can really use to describe tunneling, because there's no barrier visible. And in particular for the FRG, the way that this works is that as you flow from high values of this k to low values, you start out with something non-convex, and then it slowly flattens until, again, it's flat between these two minima. And again, what's going on under the hood is that at high k, we have very constrained fluctuations, and then as we flow down, we start to ease the constraints. Here in the second plot, there's still some non-physical regulator function. But then at some point, we hit this region where we have the stable regions are still constrained. There's still a non-zero regulator function, but the unstable regions aren't sufficiently constrained to restrict non-local fluctuations. And so there's this tension between trying to set the regulator function to 0 so we can get the physical potential, and also trying to constrain the fluctuation scale significantly enough to prevent non-local fluctuations. And so this is the problem with exact effective actions. There's a tension between those, and so we can't really choose a good point. I like to think of this as basically imagining we're clamping the potential. At high K, we have a very tight restriction on the scale fluctuations, and we sort of gradually ease this from very tight at high K to no restrictions at low K. So you might wonder, what if we just stopped at some value here? Took some intermediate value where it's still non-convex, isn't totally flat, but is actually taking into account some fluctuations. And this is referred to as coarse graining. And this actually works pretty well for perturbative weakly coupled theories, because there's this island of stability that forms here where it flows down to some non-convex potential, sits there for a while, and then flows down to the flat potential. And we heard outside of the FRG, you can also use other coarse graining techniques, like Ollie's great talk earlier this week about high temperature effective theories. But again, this even if these can solve problems like the huge uncertainties in perturbation theory at finite temperature, they introduce the scale dependence because they require a separation of scales in order to have this island of stability. That essentially, again, comes back to this requirement of a weakly coupled theory. So there's some benefits to coarse graining, but at the end of the day, doesn't solve our problem of wanting to move beyond perturbation theory. So in order to move beyond weakly coupled theories, we introduced a kind of new method where we consider a generalization of the saddle point approximation that considers just generally quasi-stationary patches that might dominate the path integral. And so if we characterize each of these patches by some bar phi here, which you can roughly think of as the quantum mean field, we can write our restricted path integral with these boundary conditions as the sum over each of these individual patches of this path integral with boundary conditions applied to this quantum mean field with this new window function here, WK. And so WK window functional is a window functional that restricts the scale fluctuations around the classical field. So this is basically our clamp here. But unlike the usual functional renormalization group, which happens to restrict fluctuations by imposing a momentum criterion, here we're directly kind of building it from first principles to restrict fluctuations around the classical field. And in particular, because it's what we know how to do, we'll consider a Gaussian window function with this regulator functional analogous to the one from the functional renormalization group, where here we choose it such that the fluctuation operator with this window function gives us something greater than the scale k squared. So again, this is the inverse scale of fluctuations here on the left-hand side. So lower bound means that we're restricting fluctuations to be small. So this, if we introduce this window function, it defines a quasi-stationary effective action, which is the effective action which integrates all fluctuations below some characteristic size. And we can write this down here on the top. And in terms of for a general path integral with boundary conditions like we saw, we can then write this path integral in terms of the sum over the quasi-stationary effective action. So importantly, we can use this technique to write down an expression for the decay rate in terms of this quasi-stationary effective action. So again, this is kind of like a generalization of the saddle point approximation, but where we're not expanding perturbatively. So because of this, so here's one thing. We can think of this visually as here these gray blobs are these quasi-stationary patches that you might imagine dominating the path integral. Here the blue shaded regions correspond to our window functions around each classical field configuration. And then if we integrate up to those window functions, we roughly get the this quasi-stationary effective action. So because of we've built it from the ground up to be the correct effective action for false vacuum decay, it satisfies all the properties we want. The QSEA is non-convex because it only takes into account local fluctuations. It's insensitive to scale because once you get this window function to enclose the size of each of these quasi-stationary patches, it stops flowing, and it can be implemented non-perturbatively. So to implement it, we use a modified functional renormalization group. I'm going to kind of just move through this quickly. Basically, we have a regulator functional instead of a regulator function. This is the regulator functional we introduced earlier that restricts fluctuations instead of momentum. And then the rest of the pieces are all basically the same as what we had previously. But and importantly, we can still use non-perturbative approximation schemes like the derivative expansion to numerically implement this exact flow equation. And so if we compare the flow equation in the local potential approximation that we found, we can kind of compare what this looks like visually to what we were doing previously. So at high K, oops, these arrows are misplaced. At high K, we have basically the same thing that we had previously. It's very clamped, and it gives us the classical potential. That's good. But then the difference is that because we have this regulator functional that's field dependent and depends on V double prime, as we start to lower the scale K, only the unstable regions end up being constrained. And so at the end of the day, when we take K to 0, these stable regions that previously we were finding were over-constrained at these intermediate values are totally unconstrained. And then in the unstable regions, the regulator is non-zero, but is sort of like the minimal constraint. Namely, these bars here are supposed to kind of represent that in those unstable regions, the regulator sets the theory to be massless. So we're sort of, compared to the previous method, we're only clamping in the regions where it's required in order to prevent convexity. And if we compare the flow equation that we got to coarse graining, we can, by transforming our flow equation back to momentum space, I just want to briefly touch on the fact that what we get is basically the usual previous flow equation. Here, this first piece is what you would usually get in FRG with a typical coarse graining scale. But with this new strong coupling that freezes, that essentially stops the flow around the pole that usually generates this convexity. So my favorite part about this technique is that the flow equation that I was showing previously, right, this is in the local potential approximation. This is just a usual just differential equation for each of the potential at each of these points. So we can simply solve it in Mathematica or SciPy with the just built-in differential equation solvers. And use this to get the quasi-stationary effective potential from the classical potential. So this is something that's exciting because it's non-perturbative, but it's something that, you know, those of us that aren't part of huge lattice collaborations and just have our laptops can do pretty easily. And I'll show you some examples of applied to this toy model of a 1D or a single real scalar. And here on the left-hand side, we're looking at the effective potentials for when we're well into the weak coupling regime. And you can see that this black line, the QSEA, and the red line, red dashed line, the one loop perturbative result, agree pretty much exactly. Notably, the QSEA is also non-convex, which is exactly what we want. So this is a great test because we know that at least at 0 temperature, the perturbative method works. And so we would want this to, it's great that this matches. It's a good test of our method. But then as we go into the strong coupling regime, and here on the right-hand side, it's pretty, I cranked up the coupling is pretty strong. We get that, as we expect, the QSEA here in black disagrees with the one loop result. And so this is kind of underscores the importance of using a non-perturbative method like the QSEA for strong coupling, because not only do they disagree quantitatively in the decay rate, but here actually the one loop result doesn't predict a first order phase transition at all. And if we go to the decay rate, here, this is the action of the bounce solution. So the thing that really is the dominant part of the decay rate. Again, we can compare the QSEA in the one loop plotted here against this thing that basically, a parameter that basically controls the perturbativity. So on the left-hand side, it's weakly coupled. On the right-hand side, it's strongly coupled. And again, we can see that in the weak coupling regime, they match very closely. Then as we head over to the strong coupling regime, they disagree, not only quantitatively, but qualitatively. So I'm just going to start to wrap up here by talking about some of our next directions that we've been working on. So this has spawned a whole hydra of possible next steps, and kind of the loose three directions we're thinking about right now are expanding the formalism that we've developed to incorporate more general regulators and more general approximation schemes. And I'm most excited about extending this to the 2PI formalism, which might let us use the vertex expansion instead of the local potential approximation. We're also working on extending this to kind of more scenarios. Mainly, the big one that we're interested in, obviously, is finite temperature, because this was all at 0 temperature, and more non-trivial field content. So we're working on this actively right now. And then, of course, then there's once we've developed these two branches, we're also planning to then apply it to these complicated questions like gravitational waves from QCD-like theories. And so I just want to wrap up by once again saying thank you to the organizers, and I get also to my great collaborators, Juna and Hitoshi. And then open the door up for any questions.
Okay, let's thank Eleanor again.
We have one in the chat.
Yeah.
Oh, chat. Here we go.
Okay, you wanna go on with the question?
Slide 7. Multiple dominant saddle points. So this is for the perturbative case. Yes.
Maybe we should actually read it out loud for everyone.
Yeah. So the question is at slide 7. So if I back up to slide 7, how do we know that we don't have multiple dominant saddle points, and how that complicate our situation? So this is a great question. And the answer is that there are more saddle points. In particular, the numerator also allows the shot saddle point, which starts at the false vacuum, tunnels directly over to the true vacuum, stays there the whole time, and then comes back to the false vacuum at plus infinity. The answer is basically just that it's subdominant exponentially, because it's sitting at the true vacuum the whole time. And in terms of the denominator, again, it's kind of the same picture, right? The bounce saddle still is there, but that it's exponentially suppressed. And so at least to the order that we typically care about these things, they're much larger uncertainties coming from other parts of this calculation. The extra saddle points that are exponentially suppressed to each other, so we usually don't use them. But in principle, you could. And then there's another question in the Q&A. Would this method of functional renormalization group work for computing runnings in field theories with non-minimal gravitational couplings that are very large? So I know that this is not my area of expertise. I don't, other than gravitational waves from phase transitions, I don't usually work with gravity. But hold on, let me. I'm not sure whether this question refers to the usual functional renormalization group or a modified functional renormalization group. But I know that the functional renormalization group in its usual form is something that is used by the gravity people. I just am not an expert on it. Yeah, the kind of two big areas in which it's been applied are the really thermal QCD type stuff, and then the high energy wizardry.
So, one more question. We have one more question from the audience. It's coming.
think the problem I missed this part, like it's more for my own understanding. So the scale independence really when you choose a window function, you need to patch, like you need to enclose the stationary patches. But like what determines the stationary patches?
Great. Yeah, this is a great question. It's something I kind of glossed over. So the characteristics you can, so the characteristic size of the fluctuations around the stationary patch. So let's see, in terms of what defines the stationary patches, it's just kind of the regions that are, yeah, they might not be stationary points of the classical action, but they are close enough that they dominate, and they may be stationary points. What determines the kind of rough size of these is just the mass around those points. And so this is why our regulator functional is based on the tree level mass around those points. This kind of gets back to the following bit that I was talking about. Right, if you look at this picture, the problem with the previous, the usual exact effective actions, like just the usual FRG coarse grained effective action, is that you can't control the fluctuations without also clamp the fluctuations in these unstable regions without putting this unphysical clamp on the stable regions. And so that's where essentially where the scale dependence came in. But here, because we're able to relax the clamp on the stable regions all the way to 0, that's how we end up eliminating the scale dependence, at least in those regions. So essentially, yeah, if you look at the regulator functional for the constant field here at the top, just because it includes the tree level mass, that's how we end up knowing that it's larger than the scale of the fluctuations around each point. And I should actually add here while we're discussing this, this incorporates the tree level scale fluctuations around each point. And so a natural question might be, what about the full quantum scale fluctuations around each point? And that's exactly why we're currently working on extending this to the 2pi formalism, which naturally has a way of expressing the full quantum scale of fluctuations in a way that could be regulated by this.
Thank you so much. I have more questions, but I'll ask offline.
Yeah, feel free to ask.
I just had one comment, Eleanor. So this way of putting some constraints introducing some constraints so that you have fluctuations under control. If I understand correctly, this method is not Euclidean, right? So you're not looking at the calculation the Euclidean way of doing the bounce action calculation.
Sorry, this method is not. We are in Euclidean space here, yeah. So we are working in Euclidean space, but once we've calculated the effective action, we can kind of straightforwardly rotate back into Minkowski space. This is something that I can explain the details more later, but there's within the direct method, it's fairly forward to do the analytic continuation.
Let me just make my comment because we are running out.
Yeah.
I think there should be a way to connect it to a well-developed formalism of constrained instantons where you introduce extra terms in a potential. And the idea is that I think for your case, it would be some derivative terms because they have to care about the fluctuation scale. And that modifies the answer in a way that it kind of removes out the effects you don't want to catch. And, so I don't know if you have thought about it or if you're aware of that, but it sounds very similar. It sounds very similar to that way of calculating things.
Quite honestly, that's not something I've thought about, but that's a great question, and so something I'd love to look into.
Okay, we can chat offline afterwards. So.
All right, let's thank Eleanor and all others.